Hello, welcome back to Piers Rocks. Today we're going to access the boot ROM code directly off this RP2040 microcontroller, and we're going to do it from Rust. So it's nothing new for a microcontroller to contain code in the processor itself within the ROM that you can call from within your applications. A few years ago I spent a lot of time working with the ESP8266 processor from Espressif, and I was working on that with quite a low level, and I became quite familiar with how to access those ROM functions directly. Here in front of you, you can see a list of some of the ROM functions that are available on the ESP8266. There's an awful lot of them, but you can see we've got standard type functions, standard memory accessing functions, standard string manipulation functions, timer functions. There's a bunch of math functions. There's an awful lot of code written into the ROM on the ESP8266. Now the ROM on the 8266 is located at addresses beginning OX4, and this file, this linker mat file, tells the linker, when you build your code and want to produce the binary, where the linker can actually find the implementations for all of the different functions that you're using. In C code, you'd normally include a header file with function prototypes for the functions that you want to use from this list. And then when the linker actually produces your binary, it has to know at what address each of those functions is located at. So this is the file that actually provides the linker with that information, and then allows the CPU to call into the load the function from the correct address and execute it. One of the benefits of this approach is that it can be much faster to access functions that are built into ROM, rather than having to load functions that are located on the flash, your code that you've written to the flash of the device. It can actually execute them directly from ROM. That tends to be much quicker. The implementations of these functions may well be optimized for the specific hardware that they're shipped on, and therefore they may be faster than standard library implementations of these functions. And then thirdly, there's a sort of minor other efficiency benefit where you don't have to include implementations for these functions within your image itself, so you use up less of the scarce flash for your device. So this is an approach that I've seen before that CPU microprocessor designers use for embedding and then locating functions within their ROM code. The Raspberry Pi developers took a different approach. Let's start off by taking a look at the RP2040 chip itself. So this is a de-encapsulated photo of the RP2040 chip produced by YouTuber Electron Update a couple of years ago. And while I don't have the expertise to be able to identify the different sections on the silicon, his view is that the ROM code that we're going to be taking a look at, 16 kilobytes, 16K of ROM code, is located in this area of the chip. He thinks we've got the RAM there, and then the two cores of the RP2040, the ARM Cortex M0 Plus cores, located here. So within this location of the chip, which is, I'm guessing, maybe about 1 millimeter long by 1/4 millimeter wide, we've got 16K of ROM code actually physically etched into the RP2040 silicon. Here we're looking at the datasheet for the RP2040, and this provides all of the details about the boot ROM from the device. So first of all, we can see that the boot ROM is limited to 16 kilobytes in size. Now I don't know if that's a limitation of the particular ARM processors that's being implemented on the RP2040, or whether it's just that was the space that the RP2040 designers decided to set aside for the ROM, but we're limited to 16 kilobytes. And it contains the code that actually starts up the processor, so we can see that it will actually boot core 0 and put core 1 into a low power and waiting mode. The boot ROM also contains the implementation for the USB mass storage device that the Pico emulates. When you plug in a brand new Pico, or you hold down the button and plug it into your host, it mounts itself and pretends to be a flash device. It's not a flash device, but there's an implementation under the covers implemented in the boot ROM that pretends to the host to be a flash device, allows files to be copied to it, and then under the covers, this boot ROM code is reflashing the device with the code that was copied to it. And then we can also see that there are some other routines located in the ROM. We've obviously got some routines for programming and manipulating the flash. That's required by the USB UF2 boot ROM code. We've also got some maths functions and some fast memory fill and copy functions, so memset and memcopy functions, and a few other bits and pieces of code. So I found myself recently wanting to access these boot ROM functions directly from Rust code, and I couldn't find a simple and straightforward way of doing that with other crates out there. So that caused me to then look into how I could access them directly from within my Rust code. If you want to access these from within C code and you're using the Pico C SDK, you don't need to understand what's going on under the covers, because all of these functions are being exposed to you through the C SDK. But I found myself looking at a much lower level of detail of this stuff, and I was really interested by what I found, and I think it's a really elegant solution the Raspberry Pi designers have come up with. We're going to take a look a little bit later at some of the boot ROM source code as well to help us understand how these functions are actually implemented and locatable within the boot ROM, and it's all open source. Unlike the standard Raspberry Pi, where some of the boot code I think comes from Broadcom and is closed source, I think one of the initial design goals of the RP2040 was that absolutely everything running on it could be open source, and that includes the code, the implementations that are burnt into, or I should say written into, etched into the silicon of the RP20 chip. If we look a little bit later on in the datasheet, it gives us some information about the contents of the boot ROM and how to access the contents of the boot ROM. First of all, it tells us that the boot ROM starts at memory address 0. So this 16 kilobytes of boot ROM code that's actually in the RP20 silicon starts at address 0. Then there's a few 4-byte pointers to functions that handle the hardware. We then get 4 magic bytes. Then there's 3 very interesting for our purposes half-word pointers, 16-bit pointers. And these are in turn a pointer to a table that can be used to look up functions that are built in to the boot ROM. The second is a pointer to a table that allows you to look up some data that's again in this 16 kilobytes of ROM etched into the chip. Actually, it's more than just data. There are some additional functions located in this table. Not all the functions are in the function table. Some of the functions are in the data table. And then the third half-word pointer is to a helper function that you can use to actually look up the location of the data or the functions that you want to access that are built in to the ROM. And this function here, located at hex address 0x18, ROM table lookup, takes 2 arguments. It takes the pointer to the table that you want to look up in, so either you want to look up in the function table or the data table, and then an index into that table. And this function will look up at that index where the function associated with that index is located and return that pointer to you, or return a null pointer if the function with that index doesn't exist. Now, the reason that these are 16-bit pointers, despite the fact this is a 32-bit processor, is just because this is a 16 kilobyte ROM that we're accessing. There's no need to use 32-bit pointers to access these functions, because they're always going to be at an address under 64k long, which is the maximum that you can address with a 16-bit pointer. Further on in the datasheet, we can actually see some of the functions that are implemented in the ROM and how we need to access them. So the code table on the left-hand side shows us an index to access a particular function. So this code is capital P in ASCII and 3 in ASCII, and that will within the lookup table, look up the popcount32 function, return a pointer to that function so it can actually be called within your code. And the index into the lookup table is computed by taking the first character, its ASCII value, as the low order byte, and then the second character as the upper order byte, and that makes up a 16-bit index that's then used to access the lookup table and return the pointer of the function. So we've got a bunch of functions here. We've got some very familiar functions here like memset and memcopy implementations and the codes for those. And we also have some flash access functions defined. Now I find myself wanting to use this reset to USB boot function. What this does is it reboots the Pico and brings it up in USB boot mode or boot cell mode or DFU mode. Essentially allows it to be updated using standard Pico update mechanisms. And the code for this is UB. Now if we look at the code, one of the things I think is really nice about this approach is this code actually has some meaning. Here, I'm speculating, but I suspect that the U stands for USB and the B stands for boot. If we go back up to the memset functions, we can see that memset is accessed using M and S. Memset aligned on a 4-byte boundary is S and 4. So yeah, these indices are not just arbitrary numbers that mean nothing, they actually have some meaning under the covers. So we're now looking at some Rust code that I wrote and I've published as an external crate that I'll link to down below to actually access this reset USB boot function from within a Rust embedded application. First of all, you can see that I'm defining a couple of constants, and these are the locations within the boot ROM of the function lookup table at 0x14, we saw that in the datasheet, and the helper lookup function, which was a pointer to that, was located at memory address 0x18. Now within my ROM object I have an unsafe, because we're doing some pretty low-level pointer manipulation in this crate, function that will call reset USB boot. And if you call this from within an embedded Rust application on the Pico, it will cause it to go into device firmware update mode. And this is a pretty straightforward function. Really, there's 4 steps. The first thing I'm doing is I'm creating a function prototype for the USB boot functions that I need to create out of thin air, or create out of a pointer to an address in ROM. And this is based on the function prototype that's listed in the datasheet. This function, this reset USB boot function, takes 2 parameters. In fact, I only need to call it with 0 and 0 to cause it to enter DFU mode. But that's the function prototype that I need in order to, when I give Rust a pointer and say this is a function I want to call it, I need to give it a function prototype. That's what this line does. The second thing that we do is we set up essentially the index or the code to find this function within the lookup table. And remember from the datasheet we saw that for this function it's character U followed by character B. Then the third thing I do is I actually call the ROM lookup function with that code. We'll look at the code within ROM func lookup in a moment. We call that to actually find a function pointer to this reset USB boot function, and we set up a variable to actually allow us to call the function at that pointer, and then we call a function, and that's the point at which the device actually gets rebooted. There's a final step here you can see which it goes into an infinite loop, and that's simply because this previous function should never return, and in fact my reset USB function I'm exposing from within my Rust crate indicates here with this exclamation mark that this function should never return. And here we have the ROM func lookup that I was calling above, and this takes 1 argument, which is a tuple, which is 2 bytes for the code. That's U and B in my example, and this is going to return a C pointer, which is the pointer to the function that corresponds to the code UB. The first thing we do again is we create a function prototype type, and this is for the lookup helper function that we're going to be calling directly on the ROM. This takes 2 arguments. It takes a 16-bit pointer to the table that we're going to use, either the function table or the data table, in this example, in this code, it's only ever using the function table. And then it also takes a 32-bit integer, which is the code that's being passed in. So again, in my example, that's U and B, and this is converted into a 32-bit integer. So U, the first character, is the low order byte, and B is the second order byte, and then bytes 3 and 4 of this 32-bit integer are unused. Now, I know I said earlier that the index into the lookup table is 16 bits, and it is, but this helper function takes that index as a 32-bit integer. The second thing we do in this function is we turn our 2 bytes, our U and our B, into that 32-bit integer, and that's set up in variable code. Then we get the address of the function table. Remember, that's not located at 0x14 hex. It's located at a location that's pointed to by the value in 0x14 on the ROM. So this code is retrieving that 16-bit value that's stored at 0x14 and setting it up in this variable so we can pass it into the helper function. We then call the helper function here. Actually, first of all, we retrieve a pointer to that helper function, and then we set it up as a variable so we can actually call it. So this ROM table lookup is now a function variable that we can call, and that's actually using the address that's written into the ROM at location 0x18. And then finally, we call that helper function. This is executing function directly on the ROM, passing in a pointer to the function table directly on the ROM, and the code that's been passed into this function, U and B, and returning the pointer to the function that's located there. If there's no function there, it would return a null pointer. And then we're using that return value back up above as the reset USB function and calling it. I hope that made sense. It's a little bit complicated. It was a little bit hard for me to get my head around just because of the different levels of indirection here and the fact that there's a bunch of 16-bit pointers and 32-bit pointers sort of flying around. But to use this Rust crate I developed, really, really straightforward, much more straightforward than any other approach I saw to do this. First thing you do is you use the crate, and then you make an unsafe call to the ROM reset USB boot function, and that will cause the Pico to reboot back into its DFU or boot cell or USB boot mode and be ready to have new firmware flashed to it. Under the covers, what's happening is we're looking up the location of the function lookup table. We're looking up the location of the helper function that will look up the reset USB boot function in that table, and we're using that function to look up in that table, and we're calling the pointer that's returned, and that's causing the Pico to reboot. Here we can actually see the boot ROM implementation. So this is the assembly code that then gets built into the code that is etched onto the RP2040 silicon. And we can see that it actually starts here, the boot ROM. So this is location 0, and this is the top of stack pointer. So these were the first 4 32-bit integers that were listed in the datasheet for the boot ROM starting at address 0. Stack top, start, NMI, and dead. Then immediately following that we have magic, and we saw these magic numbers, capital M and U in ASCII, followed by byte 1. And then the subsequent byte is the version of the ROM that's used in that particular RP2040 chip. Then immediately after that, we get the 3 half words or 16-bit pointers that we've been using here. We have the function lookup table, we have the data lookup table, so these are pointers to other areas of the ROM where these function tables and data tables are located, and then a location of the table lookup function. The reason why this has a +1 after it, I think this is indicating to the processor that that is a function, and it is using the thumb 16-bit ARM instruction set. And then we can see after a pad half word, we actually get the table lookup function, and that's obviously implemented in this assembly code here. Rather than disassemble this table lookup function, let's actually go and look at the contents of func table itself. And that's located here after the copyright statement in the ROM. And we can see we have pairs of bytes followed by a pointer, a pair of bytes followed by a pointer, and then we have that for a couple of pages here. And these are the codes that act as the index for a particular function, followed by the pointer to the function itself. So here we have the code ms for memset, and then we have a pointer to the memset function indicating that it's using thumb 16-bit instruction set. And then lower down we have ub, which is the index to the reset USB boot function. Now, some of these functions that are being pointed to here are implemented in assembly, and some of them are implemented within this Git repo as C. Reset USB boot is actually implemented as a C function. So if you want to understand under the covers what the code on the ROM is actually doing, you can look it up in this Git repo. I really enjoy looking under the hood of technology and understanding how the details that you don't normally see and are abstracted away from you are actually implemented in reality. Now, this is hardly the first time anyone has provided a lookup table for functions based in ROM code. We look back at the Commodore 64, there was a jump table, I think, at the top of the ROM space that contained pointers to the hardware functions that were implemented in the kernel ROM. And if you updated to kernel ROM, while those functions, might move around within the ROM space, the jump table would still be located in the same location. What I think the Raspberry Pi developers have done differently here, and I've not seen before, maybe done in other microcontrollers I'm not familiar with, is actually use human readable indexes into the jump table. We saw ms used for memset and ub used for reset USB boot. Some ways that's completely pointless, right? Because it's not as if you're going to be constantly writing code and you need to remember those indexes. You'll use them once. If you need to access them multiple times within your program, you'll probably store the pointer within a global variable and access that, and you have header files defining these codes for you, so you don't need to remember them. But I really appreciate the elegant approach that these Raspberry Pi developers have taken to the boot ROM functions on the RP2040. I hope you enjoyed that episode. If you did, please stick around, consider subscribing so you can see the next episode. Till next time, rock on.